November 5, 1942, 11:27 in the morning. Royal Aircraft Establishment, Farnborough, Hampshire. The autumn rain drummed against the corrugated iron roof of Hangar 7 as Barnes Wallis stood alone beside what his colleagues at the Ministry of Aircraft Production had mockingly called the most ridiculous contraption ever conceived by a supposedly serious engineer. Before him sat a wooden cylinder, precisely 18 inches in diameter, exactly 4 feet in length, weighing 960 pounds to the nearest ounce. It looked like an oversized barrel with fins, absurdly primitive compared to the sophisticated bombs, torpedoes, and guided missiles that filled the Royal Air Force's increasingly desperate arsenals. The sphere's wooden construction seemed particularly anachronistic in an age when aircraft were built from aluminum alloy and bombs were machined from hardened steel. But Wallis had specified wood for reasons that his critics could not comprehend. The material needed to be dense enough to maintain momentum during water impact, yet light enough to skip effectively across the surface. Wood provided the optimal balance between mass and buoyancy, while offering manufacturing advantages that steel could not match under wartime production constraints. Every dimension of the weapon had been calculated with mathematical precision that bordered on obsession. The 18-inch diameter represented the optimal compromise between explosive capacity and ballistic performance, determined through hundreds of equations that related sphere weight to rotational energy. The 4-foot length accommodated the spherical explosive chamber while providing attachment points for the fins that would stabilize the weapon during its unconventional flight path. The weight distribution had been calculated to the nearest pound to ensure that rotational forces would not cause structural failure during the violent spinning phase that preceded release. But this crude wooden sphere would become the most precisely engineered weapon of World War II, capable of skipping across water like a stone thrown by a child, yet delivering explosive force that could shatter the massive concrete dams that powered Nazi Germany's industrial war machine. The weapon incorporated engineering principles that had never been applied to military technology, combining the physics of stone skipping with the destructive power of 6,000 pounds of high explosive packed into a spinning cylinder that would roll down underwater slopes until hydrostatic pressure held it against its target. In 18 months, specially modified Avro Lancaster bombers would carry these wooden weapons across the North Sea toward the Ruhr Valley, where they would accomplish what 3 years of conventional strategic bombing had failed to achieve. The industrial heart of Nazi Germany, protected by massive concrete dams that seemed impregnable to aerial attack, would be breached by weapons that violated every established principle of ballistics and bomb design. The Dambusters raid of May 16 and 17, 1943, would destroy 2 major dams and damage a third, disrupting German industrial production and demonstrating that unconventional weapons could achieve strategic results that overwhelming conventional force had been unable to accomplish. But the bouncing bomb that would make this mission possible had been dismissed by virtually every military expert who examined Wallis's initial proposals as an impractical engineering fantasy that ignored the realities of combat operations. Air Ministry officials had rejected the concept as unsuitable for operational use. Bombing experts had argued that the precision requirements made the weapon impossible to employ under battlefield conditions. Even Wallis's colleagues at Vickers Aviation had expressed skepticism about his obsession with what they considered a technological dead end that diverted resources from more promising weapons development programs. The weapon that would be designated Upkeep by the Royal Air Force and codenamed Operation Chastise by Bomber Command began not with military requirements or strategic planning, but with a simple observation that Barnes Wallis made while skipping stones with his children beside a lake in Surrey during the summer of 1940. The spherical stones that bounced most effectively across the water surface shared certain characteristics that Wallis, one of Britain's most brilliant aeronautical engineers, recognized as potentially applicable to weapons design. But the journey from skipping stones to precision weapons would require solving engineering problems that had never been attempted. developing manufacturing techniques that pushed wartime industry beyond known limits, and creating tactical procedures that violated every established principle of bombing operations. The story of how Barnes-Wallis transformed a childhood game into a weapon that could destroy targets previously considered invulnerable reveals the intersection of scientific genius and wartime desperation that produced some of the most innovative military technology of the 20th century. To understand why Barnes-Wallis believed that wooden cylinders could succeed where conventional bombs had failed, you must first understand the strategic problem that confronted British military planners in 1942 and why the massive concrete dams of the Ruhr Valley represented targets so valuable that their destruction might shorten the war by months or even years. The Ruhr Valley in western Germany contained the industrial heart of the Nazi war machine. Coal mines, steel mills, chemical plants, and armaments factories concentrated in this region produced approximately 60% of German steel, 70% of German coal, and substantial portions of the synthetic fuels, chemicals, and manufactured goods that sustained German military operations. The industrial complex employed more than 4 million workers and consumed enormous quantities of water for cooling, processing, and power generation. This industrial concentration depended on a system of dams and reservoirs that regulated water flow throughout the Ruhr Valley, while generating hydroelectric power for the factories that produced tanks, aircraft, ammunition, and other military equipment. The Möhne Dam, completed in 1913, created a reservoir containing 134 million cubic meters of water. The Eder Dam, finished in 1914, held even more water in a reservoir that extended for 17 miles through the Hessian countryside. The Sorpe Dam, built in 1935, controlled water flow through a different section of the regional drainage system. British intelligence assessments identified these dams as critical vulnerabilities in German industrial infrastructure. Destroying the dams would not only eliminate hydroelectric power generation, but would also flood the Ruhr Valley with millions of tons of water that would damage factories, transportation networks, and coal mines. The psychological impact of such destruction might convince German civilians that their homeland was no longer safe from British attack, undermining morale and support for continued resistance. But conventional bombing attacks against the dams had achieved minimal results, despite repeated attempts by Royal Air Force bomber squadrons. The dams were constructed with reinforced concrete walls that were more than 100 feet thick at the base and designed to withstand enormous hydrostatic pressure from the reservoirs they contained. Direct hits from even the largest conventional bombs produced only superficial damage that could be repaired within weeks or months. Low-level attacks that might place bombs precisely against the dam faces exposed aircraft to concentrated anti-aircraft fire that made such missions suicidal. Moreover, the dams were protected by defensive measures that made conventional bombing approaches extremely difficult. Torpedo nets stretched across the reservoir surfaces prevented underwater attacks. Anti-aircraft guns positioned around the dam sites could engage bombers at any altitude from which accurate bombing might be possible. The German defenders understood the strategic importance of the dams and had invested heavily in protecting them against the bombing attacks that British planners had been attempting since early 1941. Barnes-Wallis had been studying the dam problem since late 1940, when his position as chief designer at Vickers Aviation exposed him to classified intelligence about German industrial vulnerabilities that conventional bombing campaigns had been unable to address. Born on September 26, 1887, in Ripley, Derbyshire, Wallis had established himself as one of Britain's most innovative aeronautical engineers through his work on airship design during World War I and his revolutionary contributions to aircraft development throughout the 1920s and 30s. His childhood in late Victorian England had been marked by an unusual combination of mathematical aptitude and mechanical curiosity that would shape his approach to engineering problems throughout his career. The son of a doctor who encouraged scientific inquiry, Wallis had demonstrated exceptional talent for mathematics and physics, while developing practical skills through building mechanical devices that solved everyday problems around the family home. This combination of theoretical knowledge and practical application would prove essential when he began tackling engineering challenges that had defeated more conventional approaches. His education at Christ's Hospital School and later at King's College London had provided him with the mathematical foundation necessary for advanced engineering work. But Wallace's most important learning came through hands-on experience with complex mechanical systems. His early work at Vickers, Sons and Maxim, beginning in 1913, exposed him to the cutting-edge aviation technology of the period, while giving him opportunities to experiment with unconventional design approaches that more conservative engineers avoided. During World War I, Wallace had worked on rigid airship design, developing the structural engineering principles that would later influence his aircraft work. The challenge of creating lightweight yet strong structures capable of withstanding enormous stresses had required innovative approaches to materials and construction techniques. His work on the R-80 and R-100 airships had involved solving problems related to aerodynamics, structural engineering, and propulsion systems that provided experience with the kind of multidisciplinary engineering challenges that would characterize his later weapons development work. His most notable achievement before World War II had been the design of the Vickers Wellington bomber, which featured revolutionary geodetic construction that made the aircraft exceptionally strong while remaining relatively lightweight. The Wellington's lattice-work fuselage structure, inspired by engineering principles that Wallace had developed during his airship work, proved capable of absorbing enormous battle damage while remaining airworthy. Wellingtons returned from combat missions with huge sections of their fuselage shot away, yet the geodetic structure maintained enough integrity to keep the aircraft flying until they reached friendly territory. This innovation had established Wallace's reputation as an engineer willing to challenge conventional design approaches when they proved inadequate for specific requirements. The geodetic principle, based on distributing structural loads through a network of intersecting members rather than relying on conventional frame construction, had required developing entirely new manufacturing techniques and convincing skeptical military officials that unconventional approaches could provide superior performance. The success of the Wellington design had given Wallace credibility within the British aviation industry that would prove essential when he proposed even more radical innovations for attacking seemingly invulnerable targets. But the dam bombing problem required solutions that went far beyond conventional aircraft design principles. The targets were stationary, massively constructed, and protected by defensive measures that made conventional bombing approaches suicidal. The Muna Dam alone contained more than 1 million cubic meters of reinforced concrete, with walls that were more than 130 feet thick at the base and designed to withstand hydrostatic pressures that would crush most man-made structures. Conventional bombs, even the largest weapons in the RAF arsenal, lacked sufficient explosive power to breach such massive concrete structures, while precision delivery methods that might concentrate explosive force against vulnerable points exposed attacking aircraft to defensive fire that made mission success unlikely and crew survival improbable. The German engineers who had designed these dams in the early 20th century had anticipated potential military attacks and had incorporated defensive features that made them extraordinarily difficult targets for conventional weapons. The curved design of the dam faces deflected explosive forces away from the structure, rather than concentrating them at critical points. The massive thickness of the concrete walls provided redundant strength that allowed the dams to withstand localized damage without structural failure. The foundations extended deep into bedrock, creating anchorage that prevented undermining attacks that might have been effective against less substantial structures. Intelligence reports from the Special Operations Executive and aerial reconnaissance missions had revealed additional defensive measures that complicated any potential bombing attacks. Torpedo nets stretched across the reservoir surfaces prevented underwater approaches that might deliver explosive charges directly against the dam faces. Anti-aircraft gun positions, strategically located around each dam site, could engage attacking aircraft from multiple angles while providing overlapping fields of fire that made low-level approaches extremely hazardous. Searchlight installations enabled night operations that could illuminate attacking bombers while coordinating defensive fire that had already proven lethal to RAF aircraft attempting conventional bombing approaches. Moreover, the geographic location of the dams within the heavily defended Ruhr Valley meant that any attacking force would have to penetrate multiple layers of German air defenses while navigating over terrain that offered few landmarks for precise navigation. The industrial haze that hung over the region reduced visibility conditions that were essential for accurate bombing, while the concentration of anti-aircraft weapons throughout the area created a defensive environment that had already claimed hundreds of RAF bombers during previous strategic bombing campaigns. Wallace's breakthrough had come during the summer of 1940 when he was observing his children skipping stones across a lake near his home in Surrey. He had noticed that spherical stones bounced most effectively when they struck the water surface at specific angles and rotational speeds, and that the physics of stone skipping, which had entertained children for centuries, suddenly appeared relevant to the problem of delivering explosive charges against targets that were inaccessible to conventional bombing approaches. The concept that emerged from this observation was elegantly simple in principle, but extraordinarily complex in execution. A spherical bomb, spinning at high rotational speed, could be dropped from low altitude toward a water surface, where it would skip like a stone until it struck the vertical face of a dam. The rotational energy would cause the weapon to roll down the dam face below the water surface, where hydrostatic pressure would hold it against the concrete structure until a time delay fuse triggered detonation at the optimum depth for maximum structural damage. But transforming this concept into a practical weapon required solving engineering problems that had never been attempted and developing manufacturing techniques that pushed wartime industry beyond established limits. The bomb would need to maintain precise rotational speed during flight and impact while surviving the violent forces associated with water skipping. The release mechanism would require extraordinary accuracy in timing and positioning, with tolerances measured in fractions of seconds and individual feet of altitude. The aircraft carrying the weapon would need modifications that might compromise their performance in other roles, while maintaining the precision flying capabilities essential for successful weapon delivery. Wallace's breakthrough came during the summer of 1940, when he was observing his children skipping stones across a lake near his home in Surrey. He noticed that spherical stones bounced most effectively when they struck the water surface at specific angles and rotational speeds. The physics of stone skipping, which had entertained children for centuries, suddenly appeared relevant to the problem of delivering explosive charges against targets that were inaccessible to conventional bombing approaches. The concept that emerged from this observation was elegantly simple. A spherical bomb, spinning at high rotational speed, could be dropped from low altitude toward a water surface where it would skip like a stone until it struck the vertical face of a dam. The rotational energy would cause the weapon to roll down the dam face below the water surface, where hydrostatic pressure would hold it against the concrete structure until a time delay fuse triggered detonation at the optimum depth for maximum damage. But transforming this concept into a practical weapon required solving engineering problems that had never been attempted. The bomb would need to maintain precise rotational speed during flight and impact. The release mechanism would require extraordinary accuracy in timing and positioning. The aircraft carrying the weapon would need modifications that might compromise their performance in other roles. Most challenging of all, the entire system would need to function reliably under combat conditions where mechanical failure would result in mission failure and crew casualties. Wallace began developing the mathematical relationships that governed spinning sphere behavior in late 1941, working initially with small-scale models that he tested in his garden pond. The fundamental physics involved complex interactions between rotational energy, impact velocity, water surface tension, and aerodynamic forces that affected sphere trajectory during the skipping phase. Each variable influenced the others in ways that required careful mathematical analysis to achieve predictable results. The optimal sphere diameter emerged from balancing competing requirements. Larger spheres could carry more explosive material, but required more rotational energy to achieve effective skipping. Smaller spheres were easier to spin, but carried insufficient explosive power to damage massive concrete structures. Through painstaking calculation, Wallace determined that an 18-inch diameter sphere represented the optimal compromise between explosive capacity and ballistic performance. The rotational speed requirement proved equally critical. Too little rotation, and the sphere would sink upon water impact rather than skipping across the surface. Too much rotation could cause centrifugal forces to damage the weapon's internal mechanisms. Wallace's experiments revealed that approximately 500 revolutions per minute represented the optimal rotational speed for reliable skipping performance. The release altitude and aircraft speed were interdependent variables that required precise coordination. The weapon needed to be dropped from exactly 60 feet above the water surface at an aircraft speed of exactly 220 miles per hour. These parameters were so critical that deviations of more than 5 feet or 10 miles per hour would cause mission failure. Wallace presented his preliminary calculations to the Ministry of Aircraft Production in December 1941, requesting authorization to develop a full-scale prototype. The response was overwhelmingly negative. Ministry officials dismissed the concept as impractical engineering fantasy. Military experts argued that the precision requirements made the weapon unusable under combat conditions, where aircraft operated under enemy fire and variable weather. The criticism focused on several fundamental objections that appeared to invalidate the entire concept from both engineering and operational perspectives. First, the requirement for precise altitude and speed control seemed impossible to achieve during combat operations, when pilots were maneuvering to avoid defensive fire while navigating in darkness or poor visibility conditions that characterized most bombing operations over enemy territory. The Royal Air Force had already lost hundreds of bombers attempting low-level attacks against heavily defended targets, and military planners were reluctant to approve operations that would require even more dangerous flying techniques. Second, the spinning mechanism required to achieve proper rotational speed would add significant weight and mechanical complexity to aircraft that were already operating near maximum performance limits due to the demands of carrying heavy bomb loads over long distances to targets deep within enemy territory. The additional equipment needed to spin the bouncing bombs to the required rotational speeds would reduce aircraft payload capacity while increasing fuel consumption and mechanical reliability problems that could compromise mission success or crew survival. Third, the low-altitude approach necessary for accurate weapon delivery would expose bombers to intense anti-aircraft fire that had already proven lethal to RAF aircraft attempting conventional bombing attacks against German industrial targets. The defensive environment around critical German installations had been continuously strengthened throughout 1941, with increased concentrations of anti-aircraft weapons, searchlights, and fighter aircraft that made low-level penetration missions extremely hazardous even for the most experienced bomber crews. Finally, critics argued that the entire concept was based on theoretical calculations that had not been validated under realistic combat conditions and might prove inadequate when subjected to the stresses and variables that characterized actual military operations. The controlled conditions under which Wallace had conducted his initial experiments bore little resemblance to the chaotic environment of night bombing operations over heavily defended enemy territory, where equipment malfunctions, navigation errors, and defensive countermeasures could combine to cause mission failure regardless of how sophisticated the weapons employed might be. But Wallace persisted with his development work despite official skepticism and the diversion of resources to other weapons projects that military authorities considered more promising. Using his own financial resources and working during evenings and weekends when his regular vicar's responsibilities permitted, he continued refining the mathematical models that governed bouncing bomb performance while developing increasingly sophisticated experimental procedures that validated his theoretical calculations under progressively more realistic conditions. The experimental program that Wallace conducted during 1941 and early 1942 involved testing scale models under various conditions that simulated the environmental factors that would affect full-scale weapon performance. He conducted tests in different bodies of water to evaluate the effects of water temperature, salinity, and surface conditions on skipping behavior. He experimented with different sphere materials, sizes, and weights to optimize the relationship between ballistic performance and explosive capacity. He developed timing mechanisms that could measure rotational speeds and impact forces with the precision necessary to validate his mathematical models. Small-scale tests in laboratory conditions had confirmed that spherical objects could indeed skip across water surfaces in predictable patterns when released with appropriate rotational speeds and impact angles. But translating these results to full-scale weapons that would function under combat conditions required solving manufacturing and engineering problems that had never been attempted. The precision required for reliable operation exceeded normal military equipment standards by significant margins, demanding manufacturing techniques and quality control procedures that would challenge even Britain's most sophisticated industrial facilities. The criticism focused on several fundamental objections that appeared to invalidate the entire concept. First, the requirement for precise altitude and speed seemed impossible to achieve during combat operations when pilots were maneuvering to avoid defensive fire while navigating in darkness or poor visibility. Second, the spinning mechanism required to achieve proper rotational speed would add weight and complexity to aircraft that were already operating near maximum performance limits. Third, the low-altitude approach necessary for accurate delivery would expose bombers to intense anti-aircraft fire that would result in prohibitive casualties. But Wallace persisted with his development work despite official skepticism. Using his own resources and working during evenings and weekends, he continued refining the mathematical models that governed bouncing bomb performance while developing increasingly sophisticated test procedures that validated his theoretical calculations. Small-scale tests in laboratory conditions confirmed that spherical objects could indeed skip across water surfaces in predictable patterns when released with appropriate rotational speeds and impact angles. The breakthrough that transformed official opinion came in February 1942 when Wallace conducted a demonstration test at Chesil Beach in Dorset using a scaled-down prototype that weighed approximately 60 pounds. The test weapon, dropped from a light aircraft flying at the calculated altitude and speed, skipped across the water surface exactly as predicted, before striking a floating target that simulated a dam face. The demonstration proved that the concept could function in realistic conditions rather than only in controlled laboratory environments. Air Chief Marshal Arthur Harris, commanding RAF Bomber Command, attended the Chesil Beach demonstration and immediately recognized the weapon's potential for attacking targets that had resisted conventional bombing attempts. Harris had been searching for methods to achieve decisive results against German industrial targets that conventional bombing campaigns had been unable to destroy or seriously damage. The bouncing bomb offered possibilities for precision attacks against critical infrastructure that might achieve strategic results with relatively small forces. The authorization to proceed with full-scale development came in March 1942, accompanied by the highest security classification and a directive that restricted access to information about the project to fewer than 100 individuals throughout the British government and military establishment. The weapon was designated Upkeep and assigned to a special development program that would operate independently of normal military procurement procedures to ensure maximum security and minimum bureaucratic interference. But developing a full-scale bouncing bomb proved far more challenging than the successful small-scale demonstrations had suggested. The weapon needed to carry approximately 6,000 pounds of high explosive while maintaining the precise ballistic characteristics that enabled effective skipping. The spinning mechanism required extraordinary engineering precision to achieve the rotational speeds necessary for reliable performance. The release mechanism needed to function flawlessly under combat conditions where mechanical failure would endanger both mission success and crew survival. The explosive charge presented particular challenges because conventional explosives were too unstable to withstand the rotational forces and impact stresses associated with the skipping delivery method. Wallace worked with explosive specialists at the Royal Ordnance Factory to develop a specialized charge that combined maximum destructive power with mechanical stability. The solution involved using a spherical cavity within the wooden casing that contained precisely shaped explosive materials surrounded by stabilizing compounds that prevented premature detonation during the violent impacts associated with water skipping. The spinning mechanism required developing entirely new manufacturing techniques to achieve the precision necessary for reliable operation. The sphere needed to rotate at exactly 500 revolutions per minute when released, and this rotational speed had to be maintained despite the aerodynamic forces that acted on the weapon during its flight toward the target. The solution involved a hydraulic drive system that connected to the aircraft's main engines and spun the weapon for precisely 60 seconds before release, building up the rotational energy necessary for effective skipping. Perhaps the most challenging aspect of the development program involved modifying Avro Lancaster bombers to carry and deliver the unusual weapons. The standard bomb bay could not accommodate the 18-inch diameter spheres, requiring extensive structural modifications that removed the bomb bay doors and installed special mounting points that held the weapons in the aircraft's slipstream during flight. These modifications reduced the aircraft's maximum speed and increased fuel consumption, limiting operational range and requiring careful mission planning to ensure that modified bombers could reach their targets and return safely to base. The release mechanism demanded engineering precision that had never been required for conventional bombing operations. The weapon had to be dropped at exactly the right moment when the aircraft was precisely 60 feet above the water surface and traveling at exactly 220 miles per hour. The timing tolerance was measured in fractions of a second, requiring specialized equipment that could measure altitude and speed with unprecedented accuracy while providing pilots with precise guidance for the release decision. Wing Commander Guy Gibson, selected to command the special squadron that would operate the bouncing bombs, understood that success would depend entirely on crew training that achieved precision levels far beyond normal bomber operations. Gibson had accumulated more combat experience than virtually any other pilot in RAF Bomber Command, having completed tours on both fighters and bombers before being assigned to develop the tactical procedures necessary for Operation Chastise. The squadron selected for the dam bombing mission was designated 617 Squadron and equipped with specially modified Lancaster bombers that carried the official designation Lancaster B Mark III Special. These aircraft featured the structural modifications necessary to carry upkeep weapons, along with specialized navigation equipment that enabled the precision flying required for successful bouncing bomb delivery. The squadron was based at RAF Scampton in Lincolnshire, where security measures prevented any contact between the air crew and personnel who were not directly involved in the operation. Training for Operation Chastise began in March 1943 and continued for 2 months as crew members learned to fly their modified aircraft with the precision that the bouncing bomb delivery method required. The training program emphasized low-level navigation, precise altitude control, and accurate speed maintenance under conditions that simulated the defensive environment they would encounter over the German dams. Crews practiced the attack approach repeatedly until they could maintain the required flight parameters automatically despite the stress and confusion of simulated combat conditions. The most challenging aspect of training involved learning to judge altitude accurately while flying at exactly 60 feet above water surface in darkness. Conventional altitude measurement instruments were inadequate for the precision required, forcing crews to develop visual techniques that enabled accurate height judgment, despite the disorienting effects of flying at high speed in close proximity to water. The solution involved installing simple lights under the aircraft nose that created a figure-8 pattern on the water surface when the altitude was exactly correct. Meanwhile, Wallace continued refining the upkeep weapon design based on extensive testing, that revealed minor problems with the spinning mechanism and release timing. The final version of the bouncing bomb weighed 9,250 pounds when fully loaded with explosive material and incorporated improvements that increased reliability while maintaining the ballistic performance necessary for effective dam attack. Manufacturing was limited to exactly 20 weapons, reflecting both the specialized nature of the mission and the resource constraints that affected all British military production during this period of the war. The intelligence preparation for Operation Chastise involved photographic reconnaissance missions that mapped the target dams in extraordinary detail while monitoring German defensive preparations that might affect mission success. RAF photo reconnaissance aircraft flew repeated missions over the Ruhr Valley during April and early May 1943, documenting anti-aircraft gun positions, searchlight locations, and any changes in defensive arrangements around the dam sites. This intelligence indicated that German defenders were aware of increased British interest in the dams, but had not significantly reinforced the defensive installations. Weather conditions became critical factors in mission planning, because the bouncing bomb delivery method required specific visibility and wind conditions that occurred infrequently during the spring months when Operation Chastise was scheduled. Cloud cover needed to be minimal to enable accurate navigation and target identification. Wind speeds had to remain below specific limits to prevent interference with the precise flight parameters required for weapon delivery. Moon phases affected visibility conditions that were essential for low-level navigation over enemy territory. The final authorization for Operation Chastise came on May 15, 1943, when weather forecasts indicated that conditions over the target area would be suitable for the precision flying that the mission required. 19 Lancaster bombers from 617 Squadron took off from RAF Scampton beginning at 21:30 hours, carrying their unusual wooden weapons toward targets that conventional bombing had been unable to damage despite repeated attempts over the preceding 2 years. The route to the target area required flying at extremely low altitude across the North Sea and German-occupied Netherlands to avoid radar detection while navigating with precision that would bring the aircraft to their assigned targets at exactly the planned time. Navigation at such low altitude demanded exceptional skill because normal navigation aids were ineffective when aircraft flew below the minimum altitude required for reliable radio beacon reception. Crews relied primarily on map reading and dead reckoning calculations that required constant attention to maintain accurate course tracking. The first aircraft to reach the primary target area arrived over the Muna Dam at exactly 28 minutes past midnight on May 17, 1943. Wing Commander Gibson's aircraft made the initial attack approach, flying directly toward the dam at precisely 60 feet altitude and 220 miles per hour, while Navigator Flight Sergeant Torger Terum called out distance measurements that enabled bomb aimer Flying Officer Frederick Spafford to release the upkeep weapon at exactly the calculated release point. The bouncing bomb performed exactly as Barnes-Wallis had predicted during his theoretical calculations 18 months earlier. The spinning sphere struck the water surface approximately 400 yards from the dam face and skipped across the reservoir in a series of diminishing bounces that carried it directly to the concrete wall. The weapon struck the dam face and rolled down the underwater slope until it reached the optimal depth for maximum explosive effect, where the hydrostatic pressure held it firmly against the concrete structure until the time delay fuse triggered detonation. The explosion created a waterspout that rose more than 1,000 feet above the reservoir surface and generated shock waves that could be felt more than 20 miles away. But the massive concrete structure withstood this first attack, requiring additional bombing runs that would test both the weapon system and the courage of aircrew, who had to approach a heavily defended target repeatedly while flying at altitudes that made them vulnerable to even small-caliber defensive fire. Flying Officer David Maltby's aircraft made the second attack, delivering another upkeep weapon that detonated in precisely the same location as the first explosion. The cumulative effect of two bouncing bombs finally exceeded the structural limits of the concrete dam. At exactly 1 hour and 32 minutes after midnight, the Möhne Dam collapsed in a thunderous cascade of concrete and steel that released 134 million cubic meters of water into the Ruhr Valley below. The flood wave that resulted from the dam collapse traveled down the Ruhr River at speeds exceeding 20 miles per hour, destroying everything in its path for more than 50 miles. Industrial facilities, transportation networks, bridges, power stations, and residential areas were swept away by the torrent that continued flowing for more than 12 hours after the dam breach. The psychological impact on German civilians was enormous, demonstrating that British aircraft could reach and destroy targets deep within Germany that had previously been considered invulnerable to air attack. Squadron leader Henry Maudslay led the attack on the Eder Dam, the secondary target that controlled water flow through a different section of the regional drainage system. The Eder Dam presented even greater challenges for bouncing bomb delivery because the reservoir was surrounded by hills that restricted aircraft approach angles while requiring extremely precise navigation to achieve the flight parameters necessary for weapon effectiveness. Maudslay's crew accomplished one of the most demanding precision flying feats of World War II, approaching the target through a narrow valley while maintaining exactly 60 feet altitude, despite the disorienting effects of hills on either side of their flight path. The attack on the Eder Dam succeeded with a single upkeep weapon that breached the concrete structure and released millions of additional tons of water that flooded agricultural areas and damaged transportation networks throughout the region. The combined effect of destroying both the Möhne and Eder Dams disrupted industrial production throughout the Ruhr Valley while demonstrating British capability to attack previously invulnerable targets using innovative weapons and tactics. The third target, the Sorp Dam, proved more difficult to attack because its earthen construction differed from the concrete dams that the bouncing bomb had been designed to destroy. Flight Lieutenant Joseph McCarthy's crew delivered their upkeep weapons successfully, but the explosion caused only partial damage that did not result in complete dam failure. Nevertheless, the partial breach required extensive repairs that disrupted water flow and hydroelectric power generation for several months. 8 of the 19 aircraft that participated in Operation Chastise failed to return to RAF Scampton, representing a 42% loss rate that was extraordinarily high even by bomber command standards. 56 aircrew members were killed during the mission, including some of the most experienced pilots and navigators in the Royal Air Force. These casualties highlighted the enormous risks associated with low-level precision bombing operations against heavily defended targets, regardless of how innovative the weapons employed might be. But the strategic results achieved by Operation Chastise validated Barnes-Wallis's conviction that unconventional weapons could accomplish objectives that conventional bombing had been unable to achieve. German industrial production in the Ruhr Valley was disrupted for months, while repairs to the damaged dams consumed resources that would otherwise have been available for military production. The psychological impact on German morale was significant, demonstrating that British science and technology could overcome German defensive advantages through innovation and precision rather than overwhelming force. The German response to the dam attacks involved massive engineering efforts to repair the damaged structures while strengthening defenses around critical infrastructure targets throughout the Reich. More than 7,000 workers were assigned to dam reconstruction projects that required enormous quantities of concrete, steel, and specialized equipment. The repair work continued for more than 6 months, during which industrial production in the affected areas operated at reduced capacity due to power and water shortages that crippled manufacturing facilities throughout the region. Albert Speer, Reich Minister for Armaments and War Production, later wrote that the dam attacks had demonstrated British capability to achieve decisive results through precision strikes against critical infrastructure rather than the area bombing campaigns that had characterized most RAF operations against German targets. Speer recognized that similar attacks against other infrastructure targets might cripple German war production more effectively than conventional bombing of cities and industrial areas, leading to increased defensive measures that diverted resources from offensive military production. Barnes-Wallis became an international celebrity after details of the bouncing bomb were revealed following the war's conclusion. His innovative approach to solving seemingly impossible engineering problems inspired a generation of scientists and engineers who recognized that unconventional thinking could overcome technical challenges that appeared insurmountable using traditional methods. The success of Operation Chastise demonstrated that individual creativity and scientific innovation could achieve strategic results that massive conventional forces had been unable to accomplish through overwhelming firepower alone. The engineering principles that Wallace applied to bouncing bomb development influenced weapons design throughout the remainder of World War II and into the post-war period. The concept of matching weapon characteristics precisely to target vulnerabilities became fundamental to precision weapons development during the Cold War era. Modern smart bombs, cruise missiles, and guided munitions trace their conceptual origins to the precision engineering and innovative thinking that made the Dambusters raid possible and demonstrated the effectiveness of unconventional approaches to seemingly impossible military problems. The engineering principles that Wallace applied to bouncing bomb development influenced weapons design throughout the remainder of World War II and beyond. The concept of matching weapon characteristics precisely to target vulnerabilities became fundamental to precision weapons development during the Cold War period. Modern smart bombs and cruise missiles trace their conceptual origins to the precision engineering and innovative thinking that made the Dambusters raid possible. The tactical procedures developed for Operation Chastise established precedents for special operations missions that required precision flying and innovative weapons delivery methods. Low-level penetration techniques, specialized navigation procedures, and crew training methods that emphasized precision over conventional bombing approaches became standard elements of special operations doctrine throughout the post-war period. Wing Commander Guy Gibson received the Victoria Cross for leading Operation Chastise, while other aircrew members were awarded Distinguished Service Orders, Distinguished Flying Crosses, and other decorations recognizing their contributions to one of the most technically demanding bombing missions ever attempted. Gibson's leadership during the mission exemplified the combination of technical skill and personal courage that characterized Royal Air Force operations throughout the war. The Avro Lancaster bombers that carried the upkeep weapons represented the pinnacle of British heavy bomber development, combining the payload capacity necessary for large weapons with the performance characteristics required for low-level precision operations. The structural modifications necessary to carry bouncing bombs demonstrated the adaptability of well-designed aircraft to specialized mission requirements that differed significantly from their original design parameters. The Dambusters raid became one of the most celebrated Royal Air Force operations of World War II, inspiring books, films, and television programs that brought the story of Barnes-Wallis's innovative weapon to international audiences. The combination of scientific genius, engineering precision, and operational courage that made the mission successful captured public imagination in ways that conventional bombing operations never achieved. But perhaps the most significant legacy of the bouncing bomb development program was its demonstration that individual innovation and unconventional thinking could solve problems that institutional approaches had been unable to address. Barnes-Wallis's willingness to challenge established assumptions about weapons design and bombing tactics opened possibilities that had not existed when military planners relied exclusively on conventional approaches to seemingly impossible problems. The wooden spheres that skipped across German reservoirs on May 17, 1943, represented more than innovative weapons technology or successful engineering achievement. They embodied the fundamental principle that scientific creativity and engineering precision could overcome seemingly insurmountable defensive advantages through unconventional approaches that challenged established military doctrine. The success of Operation Chastise proved that carefully planned precision operations using innovative weapons could achieve strategic results that massive conventional bombing campaigns had been unable to accomplish, despite years of sustained effort and enormous resource expenditure. 79 years after the Dambusters raid, the engineering principles that Barnes-Wallis pioneered continue to influence weapons design and special operations planning throughout the modern military establishment. The concept of matching weapon characteristics precisely to target vulnerabilities remains fundamental to contemporary precision warfare, while the tactical procedures developed for bouncing bomb delivery established precedents for special operations missions that require unconventional approaches to seemingly impossible objectives that conventional forces cannot address through traditional methods. The British engineer whose colleagues had dismissed his ideas as impractical fantasy had transformed a children's game into a weapon that changed the course of World War II. The wooden spheres that had seemed so absurdly simple proved capable of accomplishing what conventional bombs could not achieve, demonstrating that innovation and precision could overcome defensive advantages that appeared insurmountable through traditional approaches. That is how Barnes-Wallis turned wood into a supersonic weapon through scientific creativity that challenged every established assumption about bombing operations, engineering precision that achieved performance parameters never before attempted in military aviation, and tactical innovation that enabled a handful of modified bombers to accomplish what massive conventional forces had been unable to achieve against targets that seemed impregnable until unconventional thinking revealed their hidden vulnerabilities and transformed a children's game into a weapon that changed the course of the war through innovation that proved unconventional thinking could triumph over seemingly impossible odds.